Okay, so this is where we left off. We had looked at a variety of tasks in the landscape of CQA analytics, and we saw and we looked through a bunch of methods that do retrieval, that propose different models for retrieval. There are a variety of other tasks in CQA analytics, as we have already seen. All of them are listed here. So we will start by looking at a few of these tasks, and we might be able to only cover one method for each of these tasks. So we'll start with procurement, which is basically about building the QA archive from other sources, right? Okay, so let us look at a forum example. Okay, so somebody is asking a question, and this particular question is about a honeymoon trip planning and so on and so forth, and basically asking for an itinerary. And there might be somebody who is knowledgeable about the area that the person is traveling to, and he or she might provide an answer to that question, and that might appear as a second post. And then there might be somebody else who might be interested in asking for more information, or maybe even the original questioner. And then there could be somebody else seeking clarification, putting in clarifications, additional questions, and so on and so forth. So if you think of a forum contains a lot of threads, and each thread contains a sequence of posts. And if you order them in the temporal sequence, it's just one sequence, or you can order them in the form of a tree, depending on the reply structures. But we are looking at just sequences for the moment. Okay, so we have this kind of a structure, which is basically a forum contains multiple threads. Each of these threads are sequences of posts, and we are attempting to create what we want to create in our knowledge base, or the case base, actually. So which is basically a pair of question answers and a lot of such pairs. Okay, so our problem is about translating this set of threads into a set of question answer pairs. And let's look at how one could do that. And here let me just introduce a simple language model based approach for the problem, which is adapted from a CIKM 2012 paper. So they propose a generative model for creating question answer pairs or problem solution pairs. What they say is, let's assume that there is a problem language model, there is a solution language model, and a problem solution translation model, which is learned using statistical machine translation, right? And the problem language model basically assigns high values or high probabilities to those words, and these are all unigram models, high values to those words that are common in the problem. And solution language model similarly does it for solutions, right? We're using question answers interchangeably as problem and solution, but that is not to be confused. And the script goes like this. So in order to create the problem part, you just repeatedly sample words from the problem language model. Okay, and once you have done that, you have created the problem part, and now you need to create the solution part. And for that, you can sample some words from the solution language model and some words from the problem solution translation model, which is conditioned on the words that are already chosen for the problem part, right? So you've already chosen some words for the problem part. You condition the translation model on those words that are already chosen, and you can either sample from that or sample from simply the solution language model. So the script goes like this: sample problem words from this problem language model, sample solution words from either the solution language model or the translation model conditioned in the problem words already chosen. Okay, so let's look at a toy example of the generative model in action. Right, I mean, this is just a hypothetical toy example, but just to convey the spirit of the approach, or the motivation behind the approach. So the problem could be something as simple as just a 3-word thing, which is disk full problem, and the solution could be delete some files to resolve the problem, right? And you might have a bunch of meaningful words in the solution, right? So which could be delete files, resolve, and problem. The other words are mostly stop words. And you might and you have these two sources of words for the solution part. One is a translation model, which is conditioned on the words that are already chosen in the problem part. So which is basically the translation model conditioned on disk full reported, which are the words that are chosen in the problem part. And then there is a solution language model. So you might kind of intuitively say that delete and files are related to the particular problem, and so they might be better supported by the translation model, whereas the words like resolve and problem, etc., might be supported better by the solution language model. So this is basically the intuition behind the approach. There are some words in the solution that are heavily related to the problem at hand, and there are some words in the solution that are kind of generic solution words. Okay, so let's look at this ACL 2014 paper, which proposes a QA procurement framework in order to address the QA procurement from forums problem. Okay, so what they do is they take a forum. So let's say P1 is a forum, and P11 is a first post, and P14 is a fourth post in the forum, in the thread basically. So we're using forums and threads interchangeably, but generally forum is thought of as a collection of threads. Okay, so the first post in the thread is considered to be a problem, which is likely the case, and the second post, the third post, the fourth post, etc. Some of them could be solutions, some of them may not be solutions. Okay, so what we do here, what they do here is essentially exhaustively enumerate all pairs of posts from each thread in such a way that the first part of the pair, or the first post in the pair, is the first post in the thread, and the second post in the pair is any post in the thread. Okay, so you'll have P11 and P14 forming a pair, P11, P12 forming a pair, P11, P13 forming a pair, and so on and so forth. So you have P21, P27 forming a pair, which is the first post in the second thread and the seventh post in the second thread, and you create a whole lot of these pairs, right? And now you need to be I mean, having some models in order to essentially discover as to which of them are problem, which of them are solution posts, and which of them are QA pairs, and which of them are not, right? And for that, this paper uses two kinds of solution model, two pairs of models. So one is called the solution model, which is, one of them is a solution language model, like we saw in the last slide, and another one is a problem solution translation model. And this is expected to account for the solution posts, right? And there is another pair of models which are called non-solution models. So there is a problem non-solution translation model, and there is a non-solution language model. So the non-solution language model has essentially have high probabilities for those words which do not occur in solutions, but which occur in other kinds of posts in the thread, right? And similarly, the problem non-solution translation model kind of captures the interrelatedness between questions and non-solution posts in the thread, and analogously for the solution models as well. So we need to be able to learn these models. We have these pairs. We don't know which are the solutions, which are the QA pairs, and we don't know which are these models as well, right? So we need to be able to learn this. So in order to do that, this paper starts with an initialization, which is kind of a coarse heuristic, which is about assigning the first and second post pair from every thread. So P31, P32 is the first and second post in thread 3 as a QA pair, and P21, P22 as a QA pair, and P11, 12 is a QA pair, and so on and so forth, right? So whenever you have the first and the second post being a candidate, you assign them as a QA pair, as a real QA pair, and the other ones are question non-answer pairs, right? And you might realize that this one is not probably the best initialization that we can come up with, but as long as we have an initialization that coarsely takes us towards the direction that we want to take it to, if it is largely correct, then we can refine these labelings later on, which is what we will do. Okay, so what we will do is we now have some labelings which are based on this heuristic, and we learn these solution models and the non-solution models. So it's simple to learn the solution language model. For example, it's about just simply taking all the second posts in the green label pairs and learning a unigrammar language model over them. And similarly for the translation models. And similarly, if you take the other posts, if you take the other pairs, then you can learn the non-solution translation model as well as the non-solution language model. So once you have learned this, you can now forget these labelings and kind of reassess these labelings again, right? So you can look at pairs and look at how well supported they are by the solution models, how well supported they are by the non-solution models, and whichever ones are highly supported by the solution models, better supported by the solution models, you will label them as green. So you've forgotten the earlier initialization. Now you are simply using the models to reassign labels, and the other ones are going to be non-green, right? And so green stands for QA pairs. And once you do this, now what do you have? You have another labeling over which you can further refine the models themselves. So you can do the learning onto the models again. and you can do the estimation again, right? Estimation onto the other side again. So this is similar to an EM kind of framework, as you would imagine. You're learning the models in the maximization part, and you're estimating the labels in the estimation part. And once you do that enough number of times, maybe things will start converging, and then you can stop and output, right? So that's what's happening here in this paper. So what we looked at right now is basically the procurement part of it, and we've already seen the retrieval part of it, right? Retrieval methods. So now we will go further and look at some of the things that are more related to the runtime operation. Okay. So one of the problems that has been looked at is basically question quality prediction. Let us look at the problem and kind of define the problem in a more or less formal fashion, right? So you have this post. You have this question, which has the title "How to download images in Android," and you can and as people generally do, and there is a title, and then there is a detailed question. And the detailed question in this case is, I have an application that downloads images from Firebase storage and displays them. I've used async task and so on and so forth, and it's asked by a particular person, right? And there is a way to, in Stack Overflow at least, there is a way for users to rate the question. So you can kind of thumbs up and thumbs down against the question by indicating that it's well phrased or not so well phrased, or very friendly towards an answerer, or not very friendly towards an answerer, etc. So the question, the guideline that Stack Overflow uses here is, you upvote a question if the question shows research effort and it is useful and clear. That's what it says, but not everybody need to be heeding to this instruction, because people might use their own discretion and use their own heuristic to do this. So you have this. So essentially, in Stack Overflow, if you have a post, if you have a question post, you have upvotes and downvote options there, right? And quality prediction is just about predicting the quantum of upvotes a question is likely to gather. So let us say somebody has just now posted a question. You would want to have a prediction mechanism that will predict the likely quantum of upvotes that it is likely to gather, right? Okay, so let's look at this paper from ICWSM 2014, and this is by Ravi and others. So they propose a supervised approach to the problem, which is not so surprising, because essentially you will need to have some notion of quality embedded into the approach, and the best way is to use some training data. And so they train a classifier over label data and test it over held out data. And the features used in a classifier are things like question length, and this to the best of my recollection, they identified that question length is more or less correlated with quality. So longer questions tend to be better researched. And score against the topics learned over global data, score against topics learned over category level CQA data, and the global topic structure, sentence level topic scoring plus sequence information, etc. So I'm not going to details of this model because you can always look up the paper, and it's basically a supervised learning model. Okay, so that's what they do. Now there is this analogous problem in the answer part of it, which is called answer quality prediction. Let's look at the problem. All right, the work. The problem is basically about predicting the likelihood that people will like the particular answer, right? And this needs to be evaluated not just in isolation, like we did for the case of questions. Question quality prediction can be done or is expected to be done even before the question is answered by somebody, right? Whereas an answer is present only when a question is already asked, because an answer is posted against a question. So this is a slightly different problem in the sense that you have more data to work with. And this work proposes that the quality of answer is dependent on the type of the question for which the answer was posted. Okay, and they have this kind of a scoring framework, which is score of Q, A is a function of the assessment, the function of the assessment of the quality of the answer is dependent on how well it is a good quality answer for that particular question type. And you may not know the exact question type, because the question type may not be labeled as such. So you have a mechanism to kind of predict the probability that it is of a particular question type when you have the question, right? So that's what we're doing here. So it's kind of a product of two terms. One is the probability that a question is of a particular type, and second one is a probability that the answer is of a good quality, given that given that the question is of a particular type. Okay. So that's what it does. So let's look at more details about it. Okay, so this is kind of an architecture diagram, or not an architecture diagram. It's basically an illustration of how this one works. So they have a question type classifier at the top, and these are the different question types that they use. One is a definition question, the second one is a factoid question, opinion question, procedure question, reason, yes or no question, etc. And what they do is the classifier basically assigns a score for each question, for each question against a given question type. Okay, it might even assign negative scores, which is kind of slightly tricky, but that's what they do. And then for every question type, you learn a good quality scorer and a bad quality scorer. Okay, we'll not go into details of how the scorer is working, but the input-output specification, what it actually does is, given that the question is of this type, it identifies, it assesses the quality of the answer. Okay, so you have a good quality scorer and a bad quality scorer. So here, if you have a particular question which has a high value for the reason question type, okay, and then well, it has a high value for the reason question type, a reasonable value for the procedure question type, and it's definitely not a yes or no question nor a definition question. And then you now take the answer and run this answer against a good quality scorer for each of the question type, against a bad quality scorer for each of the question type. Okay, so now you have a score coming from the good quality scorer, which is basically, in this case, it says that it's not a very good answer for that particular for the recent type question. So the good quality scorer gives a score of 0.04. So you can now kind of multiply these scores. So which is the score that a question is of a particular type, which in this case it is 8.12 for the recent question type, and then the score or the likelihood that the answer is of good quality given that particular question type, which in this case is reason, right? So you now multiply these two things and you get 0.29. So if you multiply 8.12 by 0.04, you get 0.29, right? And you do that for all the possibilities, all the combinations. And now you have a set of good quality scores, a set of bad quality scores. You can take the sum of those things. So here, if you take the sum, you get 1.16. If you take the max, you get 1.17. And you look at the bad quality scorers, if you take the sum, you get 10.89. And if you look at the max, you get 7.83. So in this case, the bad quality scores tend to are seen to dominate and are much higher than the good quality scores. Okay, so this answer is assigned a label on which score, good or bad score, which of these scores is higher, right? So in this case, it is clearly going to get a label of bad, whether it be aggregated by using the sum mechanism or using the max mechanism. But these need not exactly agree all the time. Sum and max are different functions, so you might need to make a choice as to whether you want to aggregate using sum or aggregate using max. Okay, so moving on, let's look at question hardness prediction. So given a question, the task is to predict the degree of hardness of the question. And you should notice that a good quality question may still be hard to answer, right? So it's not, hardness and quality are not exactly the same kind of notion. So there is a subtle difference in the notion. A poor quality question may be vague, making it difficult to answer, and other poor quality questions might also be very silly, right? So hardness and quality are slightly different notions, and it's important to keep this in mind, and that's what distinguishes the question hardness prediction problem from the question quality prediction problem. Okay, so this task was addressed in this SONAM paper, the Social Network Conference in 2014, and the paper title is Question Difficulty Evaluation by Knowledge Gap Analysis. So what they do is a preliminary study, and they identify this observation called the knowledge gap phenomenon, which says that experts answer experts questions and amateurs answer amateurs questions. So if you plot the question asker expertise and if you plot the answerer expertise, and look at so each of these cells, is about the number of questions asked by a person of expertise 2 and answered by a person of expertise 1. So that gives you this the shading. So the deeper the shade, the more the number of question answer pairs that fall within that combination. And having plotted this, they kind of identified this kind of a trend, which is fairly evident here, in the sense that most of these question and answer levels, most of the question answer pairs are in this diagonal region, right? So the density of the color is directly related to co-occurrence, and they identify that most of the QA pairs in the corpus are within this diagonal region. And what does that mean? It means that answer experts, people, I mean, if you're an expert questioner, you write a good quality question or a good question, and it attracts expert answerers as well. Okay, so moving on. So let's look at how they do this model. So the task is about quantifying the hardness given a question. Okay, so H is a hardness level which comes from the same vocabulary as expertise levels. Okay, so expertise and hardness is kind of used interchangeably here. And if you write it out in the base form using the base rule, so you get a probability of question given hardness and probability of hardness divided by probability of question. And you can kind of ignore the other two terms, the non-conditional terms, because I mean they don't really cause a lot of. I mean the probability of hardness is going to be roughly the same for all the for all the questions, assuming that there is a reasonable distribution, and the probability of question doesn't make sense because you're trying to just assess the hardness of the question, and you're trying to do the scoring for the same question, so you can just take that out. Okay, so the probability of so what they do is the probability of question given hardness. They use an interpolation here, which is alpha times the probability of the question being of similar character as those asked by the users of expertise H, by askers of expertise H, questioners of expertise H, right? So you take the historical data from the corpus, you look at all those questions that were asked by people with an expertise level of H, and then build maybe a language model over them and find the probability of the question using that language model. And similarly, you can do that at the answerer side as well. So here, PA of Q given H is the probability of the question being of similar character as those answered by the users of expertise H from historical data. So your language model is still built over the question corpus, but your choice of questions is the subset of questions that you choose is based on the answerer's labels, right? And now that you have this, you can simply do an interpolation, which is alpha times PQ of Q given H plus 1 minus alpha times PA of Q given H, and that gives you a P of Q given H scoring. Okay, so moving on, let's see where we have reached in this whole task landscape. We have looked at procurement, we have looked at hardness of questions, we have looked at good quality questions, and we have looked at a whole bunch of retrieval methods in the previous part of this talk. Okay. So now let's move on, and we'll look at organizing QA archives, which is an important problem because QA archives may need to be manually curated for quality purposes, and you don't want to just procure everything in your forum that your algorithm thinks is useful, and the expert curator might just be overwhelmed, right? So the expert curator may have a niche field of expertise as well. So you might want to cluster, you might want to organize them in a way that the question answer pairs within a cluster or within a group are kind of coherent, so they can be given to the same expert curator who has a particular expertise in that field. So if you're thinking about IT Q&A, then maybe wireless issues are all need to be bashed together so that you can give it to a wireless expert who can look through that, right? And it's useful to cluster QA archives along topical lines in order to aid the manual curation process, as we just said. So you want to cluster QA archives. So you have a whole set of QA archives. Now, in order to cluster any kind of data set, estimating the pairwise similarities between the data points is the crux of any clustering method. That's something that is important, or that is the basic building block of any clustering method. Okay, so let's look at an example here. So this example, which shows two QA pairs, QA1 and QA2, are both related to the internet connection. Okay. And you might see that the questions are highly similar. well, I mean, the questions are not highly, the questions are not highly similar. The questions are of medium similarity because they talk about internet connection not working and LED in one case and the internet LED in another case, a power LED in one case, and so on and so forth. So it's of medium similarity. And you might see that the answers are also of medium similarity. It talks about router login page, and so there is a similarity in that aspect. And but the second answer talks about broadband cable, etc., whereas the first answer talks about broadband credentials and connect and so on and so forth. And as you might see, the root cause behind these two problems or behind these two question answer pairs are very different. One is a router authentication issue, the other one is a router loose connection. So you have medium similarity across the Q&A pairs, Q&A parts of both of these pairs, right? Now let us contrast this with another set of two Q&A pairs, which is QA3 and QA4. Here the questions are highly similar. So the question is basically talking about a library and so on and so forth. So my Java app is picking up the old Dojo libraries while I have a new version. The QA3 talks about one old version of Dojo. QA4 talks about a slightly newer version of Dojo. But apart from that, the content is very similar, right? Whereas if you look at the answers that have been proposed against them, the answers are quite different. One of them says that you should update the Java class path variable. The other one talks about deleting off a folder which contains older libraries and so on and so forth. However, you might see that the cause of these two question answer pairs are both the same, which is multiple libraries and class path. Okay. So let's kind of well, these are cursory observations, but these observations lead us to something interesting, which is basically saying that if the question part similarity, the similarities between the question parts is medium and the answer part is medium, you can kind of well, maybe say that they are of the same cause or not of the same cause, whatever it is. And in this particular case, they are not of the same cause. But in certain cases, if the similarity on one of these parts is high, then it tends to be of the same cause. And in particular, when we looked at the previous example, we saw that the same question was being posed, but there are two different ways of answering that question, right? Which is typically the case. It's not like you have a particular kind of problem and there is only one solution to it. There might be multiple solutions to it, which might be very different in character, but which might both be legitimate solutions to the problem. So similarity is sometimes localized at the A side, is what we saw. At the Q side is what we saw. The problem was the same, but the other way can also happen, which we saw in some of the question answer pairs that we got from some of the archives. Okay, so this paper now is from EMNLP 2016, and it talks about clustering QA archives by making use of this intuition that similarity could be localized on either side. So if either the question side or the answer side thinks very strongly that a pair of QA pairs need to be together, then probably they need to be together. So that's the whole idea behind this. So if you just simply write out the k-means objective function, right, for clustering, then you will have something like this. You have a summation over the set of clusters, and you have the summation over the QA pairs within that cluster, and you compute the distance between the QA pair and the centroid of the cluster, right? And so that is what the distance of QA to the centroid. And you might kind of write this out in a different manner and say that the distance of the QA pair to the centroid is probably the distance of the QA pair to the centroid on the question part plus the distance of the QA pair to the centroid on the answer part. So you simply consider the question part in the first term here and the answer part in the second term here. Now, based on our insight earlier, what we have identified is that it's probably not a good idea in order to use that insight, because similarity could be localized on either side. So you might want to take the minimum of the distances across the question and the answer part, and the minimum of the distance should guide whether they about the cluster memberships, right? So we're simply replacing the summation in the middle equation by a min function in the last equation, in the last expression, basically. So now let's look at where we have reached and why there is a problem here. The problem is that the min function is not differentiable, and we need another formulation in order to be able to handle that min function. And well, I mean, luckily we have a formulation which is and the mean between two real numbers p and q is approximated by p raised to x plus q raised to x the whole raised to 1 by x, as long as x tends to minus infinity. And we found that for most real numbers that we deal with in the question answer similarity kind of scenario, which are between 0 and 1, but not extremely low and so on. So in those kinds of scenarios, we have found that x of minus 10 or x of minus 20 is a good enough choice to get a reasonable approximation of the min function. So what we have is, we have now replaced the min function by its approximation, which is the distance of q, distance in q raised to x plus the distance in the a part raised to x, the whole raised to 1 by x. And that's what we have here. Okay, and that and essentially there is a clustering that entails from this. So basically you take this objective function and you differentiate it and essentially derive the e and m steps, the analogous to the k-means objective function, and you get a final clustering. And they found that that clustering is generally typically of higher quality, because that intuition that similarity localization could happen on either side it generally holds. That's what it says. Okay, so let's move on to the task landscape, and let's once again gray out the places that we have seen already. We have looked at procurement, we have looked at organization, we have looked at hardness prediction, quality prediction, and retrieval. And the next thing is about looking at expertise modeling. Okay, before looking at expertise modeling, we will introduce some basic technologies that are used in the methods for expertise modeling. So the first one is about HITS, which is basically a web page ranking algorithm, and these two slides will be a quick introduction to HITS. So HITS is a classical algorithm which was due to Kleinberg in 1999, and it is a web search algorithm developed around the same time as PageRank, and it is implemented within the Ask search engine. People who have been using web search engines in the 90s would definitely know about it. And it associates each web page with two scores, a hub score and an authority score. Okay, so let's look at a simple search query and try and see the motivation behind these scores. So the search query is automobile makers, and you could have a list of companies that do rankings of automobile makers and maintain lists of automobile makers, like those on the left hand side, and there could be the actual automobile maker companies, the individual companies on the right hand side. So the car rankings by Edmunds or whatever refers to a bunch of these automobile makers, refers to a lot of these automobile makers by way of links, and similar is the case with car rankings, and similar is the case with car manufacturer websites. And on the other hand, if you look at the right hand side, Chrysler or Ferrari or Fiat and Ford and so on and so forth, all of them have a lot of links from at least one or more of these good websites that maintain lists of automobile makers. So you can look at these two things as two separate kinds of web pages. One is what Kleinberg calls as good hubs, and the other ones are called as good authorities. So hubs maintain lists which contain links to good authority pages, and the authorities are actually the automobile makers themselves in this case, or in fact the individual pages of reputation, of high reputation. Okay, so let's move on and let's look at what hubs and authorities are. So we'll look at the algorithm called HITS. So I think it's called hyperlink induced topic search, if I remember correctly. So it starts with each node having a hub and authority score both set to 1.0, both set to unity. So there is no discriminating power for this scoring at the moment of the initialization time. And there are two update equations. So one is the authority update. So for each web page, the authority score is updated as the sum of the hub scores of each node that points to it. All right. So if you look at a web page for Ford, if it contains a lot of links from good hub pages, then it'll get a high authority score. And you look at the hub update, and it follows an analogous process. For each web page, the hub score is the sum of the authority scores of each node that it points to, right? Okay, and you normalize the authority scores, you normalize the hub scores, and go back and do the update step. So this is an iterative algorithm, and at some point the authority and the hub scores will start to converge, and that will be reflective of the linkage structure between the hub and the authority pages. Okay, now let's look at an algorithm for expertise finding, which builds on top of this. So it's the paper is called Discovering Authorities in QA Communities Using Link Analysis, and this was an old paper, CIKM 2007. So it's more than a decade old now. Okay, so what they do is they model askers and answerers who are both users. So users who ask questions are called askers, and users who ask type in answers are called answerers, and of course the same user can be an asker as well as an answerer. And let us look at this example illustration of activity within a QA network. So user 1 asks a question which is answered to by 3 users, user 3, user 4 and user 5, and user 2 asks a question 2, which is replied to by 2 users, user 5 and user 6, and user 2 asks a second question, which is question 3, which is answered to only by 1 user, which is answer 6. Okay, so that is a construction of this network, of this illustrative example. And what these people do in this paper is that they condense this network to form user-user networks. So if user 1 has posted a question that was replied by user 3, then there is a link from user 1 to user 3. And in certain cases, you might have multiple questions that were replied to by the same user, which in this case, the example is user 2 to user 6. So user 2 has posted 2 questions, both of which have been answered by user 6. Right, so you have a multi-edge in that sense. So there are 2 edges going from user 2 to user 6. So you create this kind of a network, which is basically a user network, and then work your way from there. Okay, let's look at what they do. So they model, they kind of draw this comparison and say that askers are hubs. So good askers attract good answerers, and answerers are authorities. Good answerers answer questions posed by good askers. So that is the assumption that they use, and essentially, given this assumption, the idea of looking at answerers and questioners or askers and associating them with 2 scores falls out kind of neatly, because it's simply an authority score and a hub score. So, and you run hits over the network and output the good authorities as experts, and that's what you do. So essentially, the good hubs are of limited usage in for the task of expertise finding, but maybe for other tasks they are useful. So output the good authorities as experts. So you take this network and get the authority scores, and take the top authorities, top users with high authority scores, and output them as experts. So that is an expert finding algorithm. So let's move on, and we will now introduce yet another web search algorithm called the PageRank algorithm, which was due to Brin and Page, and which was famously used by Google as its initial algorithm in 1998, before it took over the contemporary web search engines of that time in terms of market share. So the PageRank, in its simplistic version, is based on the random surfer model. Let's look at the random surfer model. The random surfer model is a script of a user running a web search session or a web session, basically, and it's essentially a script. It allows you to, much like generative models, it allows you to estimate some parameters which might be useful for other tasks. It may not model the reality of how people browse the web. So the web surfing model looks like this. So you choose a web page at random. So you're a user who is starting a web search, web browsing session. You choose a web page at random. Maybe you type in something, and you iterate over the following steps. So one is you sample R randomly from 0 to 1, which is a uniform distribution. And if R is less than D, so with a probability equal to D, you choose one outlink of the web page at random to visit next. Okay. So if D is equal to 0.6, so with a 60% chance, you choose one of the outlinks of the web page. So if there are 3 outlinks, each one of them is chosen with a 20% chance. And otherwise, so essentially you have a 60% chance of following a link from the present web page that you're on, and for the 40% chance, you simply choose a web page at random to visit next. And you do this over and again until your web browsing session, until you're bored with web browsing and you decide to call it quits. So the observation here is web pages that are heavily linked from other pages tend to be visited many times, right? And PageRank approximates the normalized number of visits of the web page. So if you look at if you run this random surfer model, count the number of visits that each web page is getting over millions and millions of iterations, and then you normalize the number of visits to the web page, and you will get something, and you will get what is called the page rank. Okay, so let's look at an example here. And this example has 3 web pages, A, B, and C. And A has a link to B, C has a link to A, and B and C have mutual links to each other. So now the probability of reaching A, or the page rank of A, is basically the page rank. Well, you can choose A with a probability of 1 by 3 if you do it randomly. So with a probability of 40%, if D is equal to 0.6, with a probability of 40%, you would choose A at random. Or you can reach A if you are at web page C, and then you choose to follow an outlink from that web page, which is with a probability of 60%, which is equal to D. And then if you choose to follow an outlink from C, then you have 2 options. One is to go to B because C has a link to B, and another is to go to A. So it is D times page rank of C divided by 2. Okay, and similarly you can write the other equation. The page rank of B, you can reach B by randomly choosing a web page, and there are only 3 web pages, so it is 1 minus D times 1 by 3. And then you can reach B from A, right, or from C. And from A there is only one outlink. So in all cases where you decide to follow an outlink from A, you will reach B. So that is with D times page rank of A. And if you are already at C and then you decide to follow an outlink from C, then there are 2 options. So it is D times PR of C divided by 2, right? And the page rank of C is basically 1 minus D times 1 by 3, which is a random choice probability, plus D times page rank of B. So because C has only one link into it, which is from B, and B has only one link outward of it. Okay, and this yields a bunch of recurrence equations which can be solved, and eventually you will get this page rank, these page ranks if you normalize them. So the page rank of A is equal to 0.23, which is the lowest, which is kind of expected because there aren't a lot of A is kind of outside. A has only one link coming into it, A has only one link going out of it. And whereas B and C are more heavily connected in the network. Well, it's heavily as in there are only a few links, but in relative to A, B and C are better connected. And you can see that probability of B, or the page rank of B, sorry, I'm confusing page rank and probability. So the page rank of B turns out to be more than the page rank of C, which is because B can be reached from 2 web pages, whereas C can only be reached from one of them. So there is a slight difference, and although the links, so the inward links and the outward links are all pretty much the same. The total number of links for B and C are both 3, but this asymmetry between the inward links and the outward links kind of gives you a little bit of difference here. Okay, so that's what you do in the case of page rank, and let's look at page rank based expertise modeling. So you can form a network of users, and the weight of an edge between users, U to V, is proportional to the number of times user use questions have been answered by V. Okay, and you run the random surfer model in the user network, and you choose the outlink from a user in proportion to the weights on the outgoing links. So there's a simple way of kind of like we did for the hits algorithm. We are kind of replacing web pages in PageRank by users, right? And the links between users are based on the asking answer kind of relationship between users. And the PageRank of users is indicative of their expertise. So you simply do the PageRank. Apply the PageRank algorithm on the user network that is formed by this answer-asker relationship, and you finally get some PageRank, which is kind of indicative of their expertise. Okay, so let's look at this paper called Topical PageRank. This is from Knowledge Based Systems in 2016. What they say is that not everybody is an expert in every topic, right? So there is no point in assigning an expertise score for a person. That you should assign an expertise score on a topical basis for every person. So it is better to model topical expertise. And how can you model topical expertise? You simply use topic level graphs and run separate page ranks. So you might have topic 1, and you consider only the answer-asker relationship in topic 1, in question answers from topic 1, and you get a graph. and topic 2 you model the ask-answer relationship, and you get another graph there. So topic 1 has one graph, topic 2 has another user graph, and you can run the page rank separately on them, and essentially you will get topical expertise. So that's what it is. So let's look at where we are now. We looked at expertise modeling well, a little bit of expertise identification, but although not in the context of questions and procurement, organization, retrieval, etc. And we will look at one more task, and which is not so well represented in this task landscape, and then I think we'll move on to how to generalize QA modeling, or how to put QA modeling, QA retrieval in the backdrop of more general multi-view data analytics. Okay, so moving on, let's look at this paper from ECIR 2013. Query suggestions for searching over QA repositories. So query suggestions are a pervasive tool to aid search. So if you just search for something, these days all the web search engines do it for you, like Google or Bing or whatever. So if you do Indian Institute of Tech, and then it will prompt you with a bunch of completions, which in this case is the Indian Institute of Technology and the various Indian Institute of Technologies that are out there as well. Okay. So the input is 0 or more complete words, and then there is an optional incomplete word. Even if you don't start writing technology, it will kind of give you some prompts. But if you start writing it, it will of course give you much more focused prompts. So there are 0 or more complete words and an optional incomplete word. And the idea is to give you suggestions on what should be the completions. So query suggestions are about completing the query that has been partially written. So so this paper from ECR 2013, with which I was also involved, has a motivating example to specialized query suggestions to QA repositories, which I think which, if I remember correctly, we found from the data itself. So if you look at the Android emulator and you're trying to complete this search query, Android emulator, then you could have, if you do a frequentist approach based on how frequently is Android emulator occurring in web pages, what are the words that follow them, and so on, then you might get things like Android emulator download, Android emulator free download, Android emulator Linux download, Android emulator Windows download, etc. But the key insights based on the QA analysis is that the QA documents containing Android emulator download exhibits high dispersion among the solution documents. So if you run this query over a QA repository and you find those question documents which contain Android emulator, and look at the dispersion in their Android emulator download, and look at the dispersion among their solution documents, it was found that there is a high dispersion, right? And more specialized phrases such as those with Linux and Windows have low dispersion. So which means that Android emulator download probably is a phrase that is associated with a broader set of question topics, with a broader set of questions or tasks which are represented as questions, each of which have their own kind of solutions. Whereas if you look at Android emulator Linux and Android emulator Windows download, etc., maybe they are much more coherent in the solution space because they are focused on a smaller set of tasks. So or rather in this case, Android emulator Windows download is just a very trivial task, which is about asking for Android emulators for Windows and to download them, and websites or sources to download them. So it may be desirable to specialize in the web search query or the web search query if you were to use it as a search query over QA repositories in order to prefer things like Android emulator Linux download, etc., Android emulator Linux, etc., because they are problems that have been well addressed within the repository, which essentially means that the eventual search query can probably be better answered by the repository. Whereas if you search for Android emulator download, and then you might find some solutions, and you might find that, and you might lead to user dissatisfaction in the sense that if you're a user searching for Windows, then you find a lot of documents related to Windows as well as those to Linux, and you don't want the Linux ones and so on. So this kind of in a way does some leapfrogging in terms of being able to specialize it enough so that you are able to well, in some sense it's leapfrogging. In another sense, it is to say that we'll sway the user towards those queries to which the case space has good answers, right? Okay, so in this case, if you do a QA aware kind of prioritization, you might get a different kind of ranking. which could look like this: Android emulator, Linux download, Android emulator, Windows download, etc. Let's look at the model itself. So this is basically the model here. So the score with respect to giving a phrase P in response to a query, in response to an incomplete query Q, is equal to the summation over the QA pairs, in the data set, and you look at the weights are associated with every QA pair, which is PD of QA, which is motivated from case-based reasoning. As we saw in the first video, case-based reasoning can quantify the alignment in the vicinity of Q, in the vicinity of the question. So basically, it would say that PD of QA would essentially tell you something about how well the similar questions of questions to Q have answers similar to Q as well, have answers similar to Q's answer as well. Which is basically something called case-based alignment. And so there is a case-based reasoning motivated document weights, and then there is a language model-based phrase probability. So in the raw method, you could have simply used a PD of P given Q comma A, which is basically you're using the document based the query suggestion over documents in the absence of query logs. That's if that was the case, that is what you would do. You would take the phrase and look at the support from each of the document and sum them up. Here we are looking at the support from each of the document and summing them up, but we are using a weighted sum where the weight kind of corresponds to gives higher values to those QA pairs which are better aligned in the solution space. So that kind of captures the intuition that we laid out in the last slide. Okay, so that brings us to almost so the case-based reasoning idea is that a QA pair may be considered to be of good quality if its Q space neighbors overlap with the A space neighbors. I'm sorry, I forgot about this animation part of it, which came on the top. Okay, so that brings us to the end of this part of the video, and in the next part we will look at positioning the QA analytics work, or the research in QA analytics, within the backdrop of a more general field within machine learning, which is about multi-modal analytics.